Intermediate Algebra, Section 4.2, Intersections, Unions, and Compound Inequalities. Two inequalities joined by the word and or the word or are called compound inequalities. To solve compound inequalities, we must know how sets can be combined. The first type that we will define is intersection. And the intersection of two sets is the set of all elements that are common to both A and B. The symbol that we use is similar to an and when you hear the word intersection, you should think the word and. The other way of combining inequalities or sets is the union, and the union of two sets is the collection of elements belonging to A and or B. The symbol we use is similar to a U, and you should think the word or. So let's take a look at sets that have the elements actually defined, and here we have four sets. In this first example, they're asking us for the intersection of C and D. We're looking for elements that are in C and in D at the same time, and that would be the elements 3 and 4. In the next example, they're asking us for the union. When you hear or see the symbol union, you should think or. So there's nothing as far as inspection required here. It's just putting the elements together with one little note. I'm going to put all of the elements of C down, and since I already have 3 and 4 written in the union of these two sets, you do not duplicate them. They're represented there. The fact that they're in both sets is of interest, but when we're looking at union, they only need to be listed once, and then the remaining values that are in D. The next example is the union of A and D, so we're going to put these two together. Again, if there's duplications, for example, there's 4 and 6 common to both of those, we won't include. If you can put them in numerical order, that's always a plus for someone that has to check it, but you do want to be cautious that you don't lose any value in the process. The next example I have is B intersect C. So we're looking for elements that are in set B and in C at the same time. And if you look, you should see 1 and 3 are elements in these two sets. The last example is the intersection of A and B. So we're looking at elements that are in A and in B at the same time, common elements. If you look at A, these are all even. B is all odds. Well, odds and evens are not similar, so we have no element that's common to both of these. And you can either express that with the empty set or the null set. Let's take a look at larger sets and the operations or the compound inequalities here instead of just integers like we just saw in the last examples. Here they're asking us to graph and write the interval notation for the following. For some of you, this might be awkward having the number first and then the variable, so we can rewrite that, making sure that we keep our inequality going in the same direction. 3 is less than x, or x is greater than 3, x is greater than 3. So to find the intersection of these two, let's graph each one separately. So here's our number line. We're looking at all the numbers that are greater than 3 but not including 3, and you can represent that with an open point. So we're headed off in this direction, an infinite number headed towards positive infinity. This other set is all of the numbers less than 8. We put an open point to indicate we're not including 8, but right up to it and headed on the left-hand side. Now we're dealing with the and. And is the intersection, the common point. So if we collapse these two and look where they have common values, it's the values that are between 3 and 8 that are in both of these two sets. So graphically, the intersection of these two sets would be the numbers running between 3 and 8. So that would be our graph. And then for interval notation, we would put our smallest value first, largest value. Since we're not including them, we will use the parentheses. Similar to this next one, again, if you want to turn this around, x is greater than -5. Graphically, values greater than -5. Now, instead of the open point, we can use the parenthesis from the interval notation. So here I have -5, values that are greater than -5, so I would put a parenthesis and my arrow continuing to the right. The second set of numbers that we're talking about or looking at are values that are less than or equal to 2. Because it equals 2, you'd either put a solid point, or if we're using our interval notation, we would use a bracket, and less than is continuing to the left. This is an and, it's an intersection. We're looking for common values between these two sets, and we can see here's our common area. Graphically, what would that look like? It is including the 2 because the x greater than -5 includes 2, so we would include our 2, and it would run all the way down to, but not including the 5. Interval notation, always the smallest value first and then the largest. We are not including the -5, we are including the 2. In this next example, we have an or. Again, graphically, to help us see the union of these two sets, we will graph each one separately. X is greater than or equal to 1. So here's our 1, and again, it's your choice whether you use a bracket or use the solid point. X is greater than 1 is going to continue off towards positive infinity. X is less than or equal to 0 would be here. We're including the 0, so we'd use a bracket, and it's continuing to the left, getting ever smaller, headed towards negative infinity. And the or is asking us for the union. Our solution should be elements from this set or this set. So we are not looking for common, we're just including all of the elements together. So for our interval notation solution, to describe this interval, we will start with our smallest value and our largest value. Infinity is never included, so it's a parenthesis. We are including 0. And then we are also including this set or interval of numbers with the union, so we'll just use our union symbol. Our smallest value for the other interval is here, 1. It's headed towards positive infinity. Infinity always has the parenthesis, and because we're including the 1, we'll use the bracket. Graphically, what these would look like are just the combination of these two together. So we would have 0, we would have our bracket, and to the left, and at 1, we would have our bracket continuing towards positive infinity, would be the graph of the union of these two sets. Another example here is asking us for the union of these two sets. X is less than 4. So here we are at 4. And if you prefer using the open point, close point, that's fine. X is less than 4 would continue to negative infinity. X is greater than 13 halves. If you don't like the fraction, find the decimal equivalency, which is 6.5. So here we are at 6.5. X is greater than 6.5, so it's going to continue to positive infinity. This is an or, it's a union. The union of these are elements that belong to this set, or both. If that happens to be the case, it isn't here. So our graph of this will be just these two together. And if you are an interval notation for your number lines, we would put the parenthesis at the negative, or at the 4 going towards negative infinity. We would use the bracket, kind of running in my number there, and it would continue out towards positive infinity. Interval notation, It kind of helps if you put those infinities there to help you with your interval notation. So our smallest value for this interval is negative infinity up to 4, but not including. So parentheses, we're taking the union and the other interval described as and I should back up, I'm seeing now, this was a greater than, not including, and it should have been, I misspoke, a parenthesis there. So it would be a parenthesis on our 6.5. We're not including it. Only if this had a bar under it would we include it, and it's headed towards positive infinity. So that would be our interval notation for that. These next problems aren't that much different than what we were doing, with the exception of we might have to do a little bit of solving ahead of time. So to get the interval here more concise so that we can take the intersection with this interval, we need to solve for the variable. So we'll subtract a 1 from each side. And now we're basically ready to go. They're asking us to graph and express using interval notation. So we're looking at the interval of values that are less than 6, open point, and to the left. We're looking at the interval of x values greater than negative 2. That would continue this way. And is the union, values that are in both of these sets at the same time, that are common. And the common values are going to be between negative 2 and 6. So our solution would be smallest value, largest value. We're not including either one. In an interval notation, we would put the parenthesis. In this next one, just a little more complication as far as prep. We have to solve for the variable to get the concise interval. So we'll add 1 to both sides. X is greater than or equal to 6. Add a 1 for the solution here. X is less than 3.5. Looking for the interval here with an OR, which would be our union of these two sets. Let's look at each one of these. X is greater than or equal to 6. So here we have 6. It's greater than or equal to either the solid point or the bracket, headed towards positive infinity. X is less than 3.5, so we would not include it, showing that with an open point, and it's less. This is an OR, so we're looking at values from this interval or from this interval, and not necessarily both, as long as it's from one or the other. The combined would look like a 3.5 decreasing and values of x that are 6 or greater, so that would be our graphical combination. Interval notation, we're headed towards negative infinity in this interval, so that's what we'll start with, and stopping at 3.5. Infinity parenthesis, we're not including our 3.5, or, so we'll use our symbol, this interval, which includes 6 and heads towards positive infinity. When we're dealing with fractions, those always give us a little bit of a pause, but to solve and graph this intersection of these two, let's get rid of the fractions. So looking at the denominators, there's only 3 in the denominators. If we multiply every term by 3, we'll maintain the inequality, plus we will eliminate the fractions. This 3 is actually 3 over 1. A 3 in the numerator will cancel out a 3 in the denominator, leaving us with 5x. 3 times 5 is 15, and the 3 in the numerator cancels out the 3 in the denominator, leaving a 5. Solving this, we'll first add a 15 to both sides, and then divide both sides by 5, leaves us with the set of all x such that x is less than 4. Here we have fractions again. Yuck. So determine the least common denominator, which in this case is 2. 2 times 3x leaves us with a 6x. The 2 over 1 times the 1/2, these are actually reciprocals. The 2's cancel out, leaving a 1. The 2 will cancel out the 2 in the denominator. We still have a positive times a negative will leave us with the negative. Solving for the variable, add a 1 to both sides. 6x is less than negative 6. And last but not least, divide both sides by 6 leaves us with x is less than negative 1. We're looking for the intersection of these two sets. What do they look like graphically? X is less than 4 would go to the left. X is less than negative 1, not including it, would go to the left. We're looking for the and or the intersection common values. The common value or the intersection or overlap, whatever verb you want to use or word to describe that, is here from just the second interval. That's where the values start having common between the two intervals. So graphically, our solution just will be the values that are less than negative 1. Interval notation, then, we're heading towards ever smaller values, so negative infinity. And the highest we go is negative 1, but not including that, so we'll put a parenthesis to indicate that. Next problem, very similar, just needing to solve for the variable. So on this first interval, we'll add a 7 to both sides. 6x is less than 18. Divide both sides by 6. So we're talking about all of the numbers that are less than 3. Here, we'll subtract a 4 from each side to get x by itself. And the last thing, to truly have x by itself, we'll divide both sides by 2 to give us a 4. So we're looking for the intersection between these two. What does the interval x less than 3 look like? Here is 3. We're not including it. Again, if you like using the interval notation for your non-inclusion, we use the parenthesis. X is greater than 4, number line wise. We're not including it, but we're looking for all values up to 4 and greater. And we're looking for an intersection. If we collapse these, there's nothing common between these two sets. So for our intersection, our answer is going to be the empty set or no solution for that. In this last type of problem that we'll deal with, using our interval notation and intersection, we're going to look at these functions, and they're asking us to write the domain. The domain can be all real numbers with two areas of concern. One is when your variable's in the denominator, and that's what this first example is. We do not want a denominator ever to equal 0. When you have 2 over 0, this is not possible, and mathematically it is undefined. Anytime, regardless of the numerator, if the denominator is 0, we can't do that operation. And if you look at this in the division that the fraction is representing, 0 times what gives you 2? Well, there isn't a number, and that's mathematically why we call it undefined. So when we're picking values of x to plug in here, in other words, our domain, you should be thinking the value's x, we need to avoid the denominator generating a 0. So for our restriction, we want, or I guess don't want to happen, the value in the denominator to equal a 0. And that will happen as we solve for x. That will happen if x is equal to a negative 4. Negative 4 plus 4 would give us a 0, and everything would come to a halt. If you had this value and this was in a computer program, you would get an undefined by 0 error, and your program would stop. On your calculator, you would get an error message or perhaps undefined. So, for the domain, every number under the sun is great. It can be all real numbers, with the exception x cannot be -4. Now they want us to write this in interval notation. Let's look graphically what the domain looks like. All real numbers would be, here's our number line. It's everything but -4. So here's -4. It can be all the values smaller than -4 headed towards -infinity, and it can be all of the values greater than -4 headed to +infinity. For interval notation, we will write this region or interval, which is -infinity up to -4, but not including it, so parentheses, union with all of these values, which start at a low of -4 and head towards +infinity, but of course we're not including -4, so we use our parenthesis, and infinity never has an end, so we use the parenthesis as well. So that would be the domain for that function. The other area that we are concerned about restrictions in our domain or values of x that we plug in is when the variable's underneath the radical. You always have to take, or can only take, the square root of values that are greater than or equal to 0. In other words, basically positive numbers. The square root of 9. Since square root of 9 is 3 times 3, we end up with 3. We're looking for a number times itself that gives us that number. Why we don't do negatives is, if it was the square root of -16, there's no way that I can come up with one number that is the same, which multiplies by itself to give us -16, that we can take the square root of. To get a -16, we'd have to have a -4 and a 4. We might skirt around it with a -1 times 4 times 4, but we still have that -1 in there. Nothing that we can do under the real number system. Further into your math studies, you'll see where we actually have a different number system to deal with that. But for right now, we're only interested in real numbers system. And so for our domain, the quantity underneath the radical, which is called the radicand, has to be greater than or equal to 0 since it's located underneath the radical. This domain then is just a matter of simplifying this inequality. So we'll subtract 3 from each side to start with. And last, we need to divide by a -2. Whenever you multiply or divide by -2, you need to change the direction of the inequality. Due to the multiplication principle of inequalities, the negatives cancel out, 2's cancel out, leaving x. Negatives cancel out, leaving 3/2. To write this domain in interval notation, either picture in your mind or actually do a quick sketch of what this looks like. We are including the 3/2, its values of x, all the numbers that are less than or equal to 3/2. So here we have our 3/2. We're including it, so we've got our bracket, and it's ever decreasing, so it's headed towards -infinity. That sets us up then to translate it into an interval notation. Smallest value -infinity up to 3/2, including that, so we use a bracket and a parenthesis.